There are two key things we're going to cover in this video. The first is a graphical representation that will relate to work, and as you can see there, it's about force displacement graphs. If we consider first of all just a simple situation where the force is constant, so we'll have force on the vertical axis and measured in newtons, and on the horizontal axis we'll have the distance that the object has moved. In that scenario, with the force being constant, that means that we'll see that the graph would look something along these lines. Now, one of the useful things about graphs is the different pieces of information that you can identify from a graph. And in this case, when we're graphing force versus displacement, versus distance, that idea that we've looked at before being the area under the curve, that's going to tell us something useful here. And if you think about area, it's a length times a width, but here the length and width that we're dealing with is actually going to be a force and a distance. And so if we take those two quantities, force and distance, and multiply them together, that then represents the work done by that force in moving that distance. So let's say we're looking at by the time the object gets to this distance here, it means that the total area under here is a representation of the work, or a graphical representation of the work done in moving that object or applying that force to move it through that distance. Just a brief note here as well, that would be assuming the force acts in the direction of motion. If the force wasn't in the direction of motion, then we'd still need to consider that cos theta term, and so instead of talking about the force on the vertical axis, we might talk about the the parallel component of the force that acts in the direction of motion. If we just look at a specific example of this, and we'll come back to this example in a video or two's time when we start to look at elastic potential energy, but I'll just mention it here as an example of a force versus displacement graph. Would be something like extending a spring. So in that case, we'd have the force that we're going to use on the vertical axis, still measured in newtons, and this time we don't really talk about a distance for a spring, we talk about the extension of the spring. And the quantity that we use there for extension, or the variable, is x, and the distance will still be meters. Let's imagine that in order to extend the spring a distance of 10 centimeters or 0.10 meters, we'd need to apply a force of 5.0 newtons. What happens in that case is that the force is not actually constant. The force will increase depending on how far the spring is extended, and so we'd have a line that looks like that. So you can see the force actually increasing there. So if we wanted to figure out the work done in extending that spring, we'd then need to calculate this area here. You can see that that area is not a rectangle anymore, it's now a triangle. So in this case, the work done, if you figure out the area under the curve there, is half times the base, so half times 0.1 meters, multiplied by the force on the vertical axis, or the height of that triangle, is 5, and so the work that would be done in that case is 0.25 joules. So there's a quick example of calculating the area under the curve in order to figure out the work done in a particular scenario. Now, to take this now to the second thing that we need to look at in this video, that quantity that we're going to deal with now is power. Now, there are two ways to think about power, or two things to keep in mind. Power is either the rate at which work is done, but if we recall that work and energy, or if you do work on something it gains energy, we can also consider that power is the rate at which energy is used. So in both cases we're looking at the rate So it's either the work being done or the energy being used. Sorry, which energy is used. Now the equation that we need to deal with here, the symbol that we use for power is a capital P, and so that's just simply the work done over the time taken, so P is equal to W on T. Now interestingly, that equation doesn't actually appear in the data booklet. I'm not quite sure why. It's a fairly important one when looking at power, but maybe just something to keep in the back of your mind in terms of the definition and how else you can calculate power. The units of power are watts. The symbol that we use for watts is a capital W, so just be careful here. You've got work being capital W, watts being capital W. One's a quantity, one's a unit. Should also mention too, W we sometimes use for weight, so you really do need to be careful about what the W means in the context that it's being used. If you look at the equation on the left hand side, it's not hard to see that 1 watt is the equivalent of 1 joule per second, and that again ties in the rate at which work is done. So the rate, the number of joules per second is the amount of power, or the number of watts that are being done. If we take this a step further though, if we consider now that work is equal to force times displacement, and here we're just going to assume that the force is in the direction of motion, so in other words the value of theta is equal to 0, so that cos theta term will be equal to 1, so W is equal to Fs. We can substitute that into our equation, so P being equal to W on T, we can instead write that that's Fs on T. So we've just substituted in Fs instead of W. I'm going to just slightly alter that to make it a little bit clearer, to identify that we've got S over T as a separate quantity that we could state there. And if you recall, a distance over time is a speed. So S over T is equal to a speed. So that means that we can say that power is equal to force multiplied by the speed that the object is moving. That's the equation that is included in the data booklet. So power being equal to force multiplied by the speed with which the object is moving. So power is a fairly useful quantity. It tells us how much work is being done, how much energy is being used. So you might have heard of watts being used for a number of scenarios, so things like light bulbs, the wattage of a light bulb, so how many joules of energy a light bulb is using per second. You can also talk about the power of a car engine, so how many kilowatts a car engine has, so again how quickly it's converting chemical potential energy into kinetic energy. So power is an important concept, and one that we'll look at through a few examples in class.